Okay, welcome back everybody. So in this video we are still looking at page 109 in the workbook, and we're going to start with a definition that relates back to the preliminary example that we did on this same page. Okay, so it starts us off with a vector field and the same situation that we encountered in the preliminary example, the situation where it's possible to find a function, little f, whose gradient is equal to the vector field that we started with. Okay, we're going to give names to some of the terms in this situation that we're describing. Okay, so if this is true, then we call the vector field a gradient vector field. Another word for it is a conservative vector field. Those just mean the same thing. Okay, and we also give a name to the scalar function f in this situation. It's called a potential function for the vector field. Okay, and what this leads to, and this also relates back to the preliminary example we did a minute ago, is something called the fundamental theorem of line integrals. Okay, so suppose that we're in this situation of having a vector field capital F where we can find a scalar function whose gradient is equal to it. Okay, we have something then that's called the fundamental theorem of line integrals. Let's read this together. So we're going to start with a curve C that has some nice properties. It's smooth. And we have a starting point P and an ending point Q. And we'll suppose that capital F is a gradient vector field, one that has this special property that we can find a scalar function whose gradient equals the fields. Okay, if all of this is true, then we can calculate the line integral of our vector field in kind of a special way. First, we'll make the observation that since our vector field is equal to the gradient of a function, this line integral is exactly the same as writing just the gradient of little f dot dr. And we can calculate this line integral by just substituting in the starting and the ending point and subtracting them. You might notice this was the same technique that we used to calculate the line integral back in our preliminary example. Okay, now a couple of important comments to go with this theorem. Okay, so starting with the first note here, the thing that's special about a line integral in a conservative vector field is that it depends only on the starting and the ending point. Okay, totally doesn't matter what the path is that we take between those points. Okay, and so for that reason, we call conservative vector fields path independent. All that matters is that starting and that ending point when we calculate the integral. Okay, another nice property that conservative vector fields have is the following. Let's suppose that C, the curve that we're integrating along, happens to be a closed curve. And what we mean by that is just a curve that starts and ends at the same point, maybe something like this. Okay, so we could pick a point on the curve and think of that as our P and our Q. Okay, referring back up here to the theorem. Okay, so my question to you is this. If you took the equation up here in the fundamental theorem and P and Q happen to be the same point, what would f of Q minus f of P equal? Well, it would have to be 0 if Q and P are the same point. And so what that means is that in a conservative vector field, if you integrate around a closed curve, you are always going to get 0 for the value of your integral. Okay, and then one more very important comment here. It's important to realize that this theorem only works in a very special situation, only when it's possible to find a potential function, little f. Okay, and a little later on, we will talk about a systematic way of deciding when we can do that and how to actually calculate that function. Okay, this concludes our discussion, our introduction of the fundamental theorem of line integrals. If you're interested, there is a derivation of where this fundamental theorem comes from at the top of page 110, and you are welcome to look at the written